And the linear relationship over here is Fs is equal to Ks. Okay. Where Fs is the spring force, K corresponds to the stiffness, and S is the what we call position, what they call, yeah, spring position. Okay, I did. So the work on the spring we usually express as US will be equal to half Fs multiplied by S. Okay. So note, as we have written before, is Fs is equal to Ks. So therefore, US is equal to half. So if I'm going to replace, so we're going to half. This is Ks multiplied by S. So this is half As squared. Okay. So when you scratch a spring, this entire term, okay, is equal to minus half multiplied by stiffness K, and this will be equal to S2 squared minus by S1 squared. Okay. It's minus because the spring force, right, is always opposed to the what? Applied force. Can you all do me a favor? On this diagram over here, put down here, this is your S1. And down here, this is your what? S2. Okay. S1 is the one that's nearer to what? To 0. Okay, so you will not get confused later on. So this chapter, the term use is very different. Kinetic energy is in terms of T, or we call it T. Work done is what we call U. Okay. Now there are forces that do no work. Okay. Forces that do no work. Okay, there are some forces that they do no work. Okay. So some external forces do no work. Example, reaction forces at fixed support. Okay. They do no work as displacement is equal to what? 0. Then another one is normal and frictional forces. Acting on a rolling body. without sleeping. Now over here, the emphasis is what? Without sleeping. So for this case, the work done is also 0. Okay, without sleeping, the highlight. Let me highlight this. Without sleeping. So the last one are your internal forces. Okay, do not do any work. And the reason why, because they always act in equal and opposite directions. Okay. So therefore, the sum of their work is also equal to 0. Now, the next thing that we are going to look at, but now we can see 3 things, okay? At a fixed support, normal and friction force, acting on a rolling body without slippage, and your internal forces. Okay. Now, the next thing that we're going to look at, okay, is the work of a couple. So I'm going to get this diagram again. So what you see over here is you have a rigid body and you have forces. Okay. And these forces is generating a moment. Okay. And what you have over here is the R over 2 are your perpendicular distance. Okay. So for this case, the rigid body is subjected to a couple, and not just to a couple, an experience. Okay. And they experience the general plane motion. And the two couples or couple, not couples, the two couple forces do work. Okay. Only when the body or when the rigid body, undergoes rotation, okay, i.e. non-static. So it's moving. Okay. Remember the previous statement we spoke about, if it's coupled, if it's not moving, then it does no work. For this case, it's a couple and rotating about 0.00, you're generating a moment, and you also have a what? Rotation. Then you are doing work. Okay. So for this case, we have UM work of a coupled moment is equal to the integration between the two limits of θ1 and θ2 moment d theta. Okay. Now m, or m for this case, can be a function of theta. Okay. However, when m is a constant, okay, when m is a constant, then what we see is the work done due to the moment is equal to m bracket θ2 minus θ1. And always remember where theta is in what? It's in radians. So the work of um, okay, is positive when θ2 is greater than θ1 and both are positive. Now we are going to use the principle of work and energy. Okay. And the governing equation which is equal to T1, okay, plus by the summation of work between 0.1 and 0.2, and this is equal to T2. Okay, so as you can see, T represent kinetic energy, U represent the work done. Okay, so if you have to remember anything, this is a good thing to remember. So we're going to solve systems of mechanical system using the principle of work. Okay, enough of this theory. Let's look at an application, or let's look at a question. This question is in your avenue to learn. Okay, so this is our okay. At the beginning, it can look a bit overwhelming with a system like this, okay, but it's by no means difficult at all. You guys have done the worst already, okay, for this course, okay. The wheel and the attached reel have a combined mass of 25 kilogram. Okay. So this is our so-called our wheel. Okay. And over here, there is our reel. Those of you that go fishing, you will know this very well. Okay. And has a radius of gyration about the center of Ka. Okay, so this is where point A is. So radius of gyration Ka is equal to 0.15 meters. Okay. And we know I just mentioned to you that I is equal to m what? K squared.